Well, welcome everybody to our calculus notes for section 4.3 on Riemann sums and definite integrals. So the definition of a definite integral is related to what we've been doing in the previous section. It says the definite integral is the number to which all Riemann sums tend as the number of rectangles approaches infinity and as the width of all rectangles tend to 0. So if f is defined on the closed interval from a to b, then the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I delta x sub I is equal to the definite integral from a to b of f of x dx. So this is a super powerful thing, and it's taking our pre-calculus into calculus here, and we're calling this a definite integral. Now as you try to find some of these things, remember that delta x sub I is just going to be the b minus a over n, okay, relating to the a and the b right here. And if you want to find c sub I, this is going to be a plus I times delta x. Okay, so you can take all those and kind of substitute them in there, so you can have the limit as n approaches infinity, the sum from I equals 1 to n, and it's going to be f of a plus I delta x, and then times delta x, and that'll be sub I there. All right, so we call a the lower limit of integration and b the upper limit of integration. So when we find a definite integral, we are going to get a number. When you were finding indefinite integrals, you were getting a family of functions, and that was with the result of the plus c. So if we want to write this limit as a definite integral, we see right here the c sub i's and the delta x sub i's, and you see the summation and the limit as n approaches infinity. So all of this is going to become the definite integral. Okay, now it's on the interval negative 2 to 4, so it's going to be the definite integral from 2 to 4 of my function. So we're really just going to replace x for c sub I. So it's going to be 2x and then times x minus 1 squared. And then the delta x sub I is going to change into dx. So this is the calculus notation for that limit. So let's use the limit definition now to evaluate our definite integral. So we're going to go backwards here. So here's the definite integral from negative 2 to 1 of 2x dx. Okay, so here's our function 2x, and we're going here from negative 2 to 1. And so what we're looking for now is the area between the function and the x-intercept in between negative 2 and 1. And so again, we're going to think about using our rectangles here. And notice our partitions can be anywhere. So I'm just going to draw a couple of them so we can see what we're doing. Okay, so we're going to go ahead and find the definite integral from negative 2 to 1 of 2x dx, and jumping straight to our limit here. So the limit as n goes to infinity of the sum from I equals 1 to n of f of c sub I. So 2 times, well, we got to find our c sub I. So let's go ahead and do some of that work over here. And remember, before we do any of that, we need to find delta x sub I. And that's just going to be delta x. And so what we're going to do is take our interval and go 1 minus negative 2 over n subintervals. So that becomes 3 over n. And if we look at this, we're going to use right endpoints. Okay? So it's always easiest just to use our right endpoints. And so in that case, remember we wanted a plus I delta x. Okay, so a is negative 2 plus I delta x. So that's going to be 3i over n. Okay, so we're going to substitute that in for our c sub I. So that's negative 2 plus 3I over n times delta x, which is 3 over n. Okay, so this is how you find your definite integral. We've got to find this limit. So let's go ahead and do that work here. We'll distribute everything. Okay, so the 2 is going to go in. So we have negative 4 plus 6I over n. And now let's go ahead and distribute the 3 over n here. Okay, now let's go ahead and evaluate this sum. We'll still have our limit. So the negative 12 over n changes into negative 12n over n. And then the 18I over n squared is going to be 18 times n squared plus n over 2n squared. And if we were to find this limit here, our n's would cancel, so this would become negative 12. And here, exponents are the same, so it's 18 over 2, so plus 9. And we get negative 3. Okay, so the definite integral from negative 2 to 1 of 2x dx equals negative 3. Now wait a second. Negative? How can a negative number give us an area? Well, it turns out that this is not an area. Now you'll notice one thing we did differently here is that this function fell below our x-axis, and so when we found this, we didn't account for our negative numbers. We're going to learn how to deal with that a little bit later. Let's talk now about definite integrals as an area of a region. So we need to stipulate if f is a continuous and non-negative on your closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equal a and x equals b is given by the definite integral from a to b of f of x dx. So it's very important that this has to be continuous and non-negative. Then the definite integral on the interval gives you the area. Okay, so it is the limit of the Riemann sum for any partition of f. So here, write the area of the region bounded by the graph of f of x and the x-axis on the intervals shown using a definite integral. Okay, so first we want our limits of integration here. So this is going to be from 0 to 4, so the definite integral from 0 to 4 of our function 4x minus x squared with respect to x. Okay? And that's all we have to do. Now notice this was non-negative on the interval, so this actually will give us the area that we're looking for. Now in example 4, it says sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. Okay, so we know that this is going to go from 1 to 3, so from here to here, and it's going to be of the function 4. Well, that's just a horizontal line. Okay, so you can evaluate this definite integral by finding this area, and we can use geometric formulas to do this. And this is a rectangle. Okay, and so it's just going to be 4 times 2. And so this area is 8, meaning this definite integral is 8. Now our next one goes from 0 to 3, and that's going to be of x plus 2. So let's plot the function x plus 2. So it's going to start at 2, and it's going to go up, rise over run, right, up 1 over 1. Okay, so there is our function. And it's going to be bounded by the vertical lines x equals 0 and x equals 3 and the x-axis. And now we're looking for this area, and this is a trapezoid. And we'll recall that the area here is 1/2 B1 plus B2 times the height. Now notice it switches a little bit. We're going to call this a base, and then this one's going to be a base, and then the height is going to be right here. So here the area is going to be 1/2 times, well, this height gives us 5, and then the other base here was 2, and then the height is the difference in the interval, which is just 3, and so this area looks like 7 times 3, 21 over 2. Okay, so the definite integral from 0 to 3 of x plus 2 dx is 21 over 2. All right, let's try our next one. So here we're going from -2 up to 2 of the square root of 4 minus x squared. Okay, well, we know here that if y equals the square root of 4 minus x squared, if we squared this, we would have y squared equals 4 minus x squared. And we add x squared to the other side, so x squared plus y squared equals 4. Hey, we have a circle, okay, where the radius is 2 and the center's at 0, 0. So there's the center and 2 for our radius. Okay, so we're going to try to find this area. Well, this is a semicircle, so your area is going to be 1/2 times pi r squared. So it's half area of a circle. Now r in this case was 2, so the area is going to be 1/2 pi times 2 squared. So that's going to be 4 times 1/2, or 2 pi. And so we know the definite integral from -2 to 2 of the square root of 4 minus x squared equals 2 pi. All right, so that's how you can find definite integrals using geometric formula. All right, next we're going to talk about some properties of definite integrals. So if we're looking at this definite integral, the limits of integration are from a to a. And if the upper and lower limits are equal, then the definite integral is going to be equal to 0. In other words, there's not going to be any area in there if we go on the interval from a to a. So when it's the same, it equals 0. Now, in this case, if we reverse the limits of integration, we actually reverse the sign of our integral. So we'll just say that this is the integral from b to a and of f of x dx, and that's going to equal the opposite, or the negative, of the integral from a to b. Okay, so if we switch the limits of integration, then we switch the sign as well. All right, next, the additive interval property. So if we have an interval from a to b, and we have an interval from a to c and then c to b, if we can add both of these up, then we get the interval of the first one. So this one's a little bit easier if we look at a drawing here. So I'm just going to put a little coordinate grid here, and we'll just say that a is right here, and then here is b, and that c lies somewhere in this interval. So we'll just call it right here. Now, if I draw a function that's on this interval, okay, if I want to find the entire definite integral from a to b, I can simply add up my integral here from a to c, and then from c to b. Okay, so we can just add those two intervals together to get the one big interval. Another property is the constant multiple property. So if k is a constant multiplying by your function, you can actually pull that constant outside of your integral. The additive function property says if we have the definite integral of two functions being added together, dx, well, we can actually split those two functions apart and find the definite integral of each one separately and then add them together. Another property is the preservation of sign property. And it says that the definite integral of a function from a to b is going to be greater than or equal to 0 where the function itself is greater than or equal to 0. So if we're looking on an interval here and we have our function is positive, okay, then I know that the definite integral is also going to be positive. Okay, so the preservation of inequality property states that the definite integral from a to b of f of x is less than the definite integral from a to b of g of x, where f of x is less than g of x. So the functions and their integrals often have the same types of properties, same signs, and then the same inequalities. So let's use the properties here to evaluate some of these integrals. So in this case, we're looking at the definite integral from pi to pi of sine x dx. Okay, well you'll notice here that this interval is the same. And so this has to equal 0 following this one right here. In our next one, we have the definite integral from 3 to 0 of x plus 2 dx. Now always be careful when your lower limit of integration is actually a bigger number than your upper limit of integration. What this is going to mean is we're actually going to be reversing the sign. Now if we look back, okay, here we have the definite integral from 0 to 3 of x plus 2 dx, and that equals 21 over 2. So let me bring that over. Okay, so we can see here that the only thing that actually switches is the limits of integration. So instead of going from 0 to 3, we're going from 3 to 0, and so what we do with that is we just negate our definite integral. So this would become negative 21 over 2. Alright, in our next one we have the definite integral from negative 1 to 1 of the absolute value of x with respect to x. So what we want to do here is we're just going to draw a little sketch of what this looks like. So absolute value of x looks like this. We have our vertex there at 0. And if we want to go from negative 1 all the way up to 1, okay, so this is a geometric shape that we don't understand what to do with. But if we were to split these into two geometric shapes, we could see that we have two triangles here. And so what we're really going to do here is split up this integral using the additive function property. And so we're going to write this is negative 1 to 0, okay, and then this function right here is negative x. And then plus the definite integral from 0 to 1 of this function, which is positive x. And we have our dx's in there just so that we can take that definite integral. And if we're looking at this, okay, we know this is a triangle, length of 1 and 1, so 1/2 base times height. That gives me 1/2 here. And then the same thing for this one, 1/2 base times height, so it's 1/2 plus 1/2, or 1. Alright, so there's some basic ways to use these properties of definite integrals to evaluate them. Alright, in our next example it says evaluate the definite integral using the given values. So here we're told that the definite integral from 1 to 3 of x squared dx is 26 over 3, and that the definite integral from 1 to 3 of x dx equals 4, and the definite integral from 1 to 3 of dx equals 2. And it says go ahead and evaluate this definite integral from 1 to 3 of negative x squared plus 4x minus 3 dx. So the first thing that we're going to want to do is separate these out. So we see different terms here of our polynomial. We're going to split into 3 different definite integrals. So this will be negative x squared dx, and then plus the definite integral from 1 to 3 of 4x dx, and then plus definite integral from 1 to 3 of negative 3 of negative 3 dx. Okay, so once we've split it up, now we can go, that was using the additive function property. Okay, so now that we've split these up, we can go ahead and take out our constant multiples. So this has a negative, so we're going to pull that out right here. And then here we have a 4, so we're going to pull the 4 out. And then here we're going to pull out a negative 3. So this is the constant multiple property. Now perhaps I should back up a little bit. Remember, we were already told what some of these definite integrals were. So this was just x squared. So when we looked at this function, we wanted to get x squared by itself, and we've done that. Okay, we wanted to get x by itself, and we've done that. And then we wanted to get dx by itself, and we've done that as well. So now we know here this is going to be negative. Well, the definite integral of x squared is 26 over 3. Okay, and then plus 4 times, well, the definite integral from 1 to 3 of x is 4. So 4 times 4. And then minus 3 times the definite integral from 1 to 3 of dx, which is 2. Okay, and so using that substitution, we can go ahead and figure this out here. So this is negative 26 thirds. Okay, this is 16, so we'll multiply that by 3 and get 48 thirds. And this is negative 6, so we'll multiply that by 3 and we'll get negative 18, so negative 18 thirds. And if we add all this up, we end up with 4 thirds total. And so this right here is the definite integral from 1 to 3 of negative x squared plus 4x minus 3 dx. All right, in our next example, we want to simplify the definite integral. So notice it doesn't say evaluate. We're just looking to simplify. So now we want to take those properties and see if we can rewrite this as a single definite integral. So we're going to go backwards a little bit and combine these. So here we have from 1 to 10, and then this one picks up from 10 to 12. And notice it is of f of x, so that function is the same. So we went from 1 to 10 and then 10 to 12, and so we know that we can add these together. And so this is going to be from 1 to 12 of f of x dx. Okay, now sometimes it's going to be helpful to just draw a picture. So here was 1, here was 10, and here's 12. And for f of x, you can just draw any function. It doesn't really matter. So here would be the first definite integral, and here would be the second definite integral. And you can see that we can just add them together, and we're going to get this definite integral right here simplified. All right. In our next one here, let's go ahead and draw our picture first for this one. Okay, so this is from 10 to 2. So 10's over here, and 2's over here. And then this one is from 13 to 10. So 13's over here, and 10's over here. Okay, so we'll just draw our function again. Now, in this one, you have to notice that we're going backwards from 10 to 2, and then backwards from 13 to 10. So really, if we went from 13 to 10 and then 10 to 2, we could rewrite this as going from 13 backwards to 2. And then this is going to be of f of x dx. Now, we usually don't like having the larger limit on the bottom, so we're going to switch this around to finish our simplification. And to do that, we're going to make it negative. So negative definite integral from 2 to 13 of f of x dx. So we like to switch that around going in the correct direction. Now, just as a side note, you could have noticed that this was going backwards in the first place. So instead of going 10 to 2, you could have switched this and gone from 2 to 10 of f of x dx, as long as you make it negative. And you could have done the same thing right here. From 13 to 10, we could have switched that and went 10 to 13 of f of x dx, as long as you made it negative. Then at this point, you could have factored out the negative, so that would have been plus there. All right, and then you could have seen that it went from 2 to 10 and 10 to 13, so your final answer would have been 2 to 13 of f of x dx. Okay, so whether you took the negative out first and switched the limits, or you just thought about it a little bit differently and then switched the limits, either way, came up with the same answer. Okay, for example C, let's go ahead and draw a picture of what's going on here. Now notice this one's going to be from 6 to 2, so here's a 6, and then here's a 2 of f of x. Okay, so that's going to look like that. Oh, and notice the direction here. It's going backwards, giving us that negative number. And then the next one goes from negative 4 to 6. So here's negative 4 to 6. So I'm going to draw f of x. Okay, and so negative 4 to 6 is going to go all the way from here on over. So what this has the effect of doing, it adds up all this area from negative 4 to 6, and then it backtracks and subtracts it all the way from 6 to 2. And what we're left with then is the actual area being right in here. Okay, you guys see that? So we went from negative 4 to 6, and then backwards from 6 to 2, and so all of this is just like going from negative 4 to 2 of f of x dx. Alright, so a little bit tricky there, but hopefully you can see this visually what's happening. Now, another way to think about this is we can change these limits of integration around. So we could have rewritten this as being from 2 to 6. That would change our sign. And then that would be of f of x dx. And then this here would be from negative 4 to 6 of f of x dx. And that's added together. Now, if we switch this around, we can see this a little more clearly. So it would have been negative 4 to 6 f of x dx, which is the second definite integral, and then it would be minus the integral from 2 to 6 of f of x dx. So again, you can see we're going all the way from 4 to 6 of our function, but then we're subtracting everything from 2 to 6. And so that is going to leave us with negative 4 to 2 of f of x dx. So it's just a more numerical way of looking at this, but either way we come up with the same answer. Alright, so that is properties of definite integrals and how to evaluate definite integrals using them, and also how to simplify definite integrals using the properties.